right.
All right. Welcome, everyone.
Hello, everyone.
Thank you for joining us today. We're going to present some topics on UAV applications with MATLAB, PX4, and Unreal Engine. My name is Ronald George. I'm a senior application engineer here at MathWorks. With me, I have Mihir.
Hello. Yeah, I'm Mihir Acharya. I'm a senior product manager for autonomous systems, specifically navigation, UAV applications. And today we are going to show you some cool demos that will include simulating UAVs in photorealistic simulations, as well as deploying controllers directly on a drone. If you can see, we have a drone right here in the frame.
Right.
Yeah, and we'll be deploying controllers from Simulink directly onto this drone. And Ronald will be showing some cool demos for that.
Yeah, we have a really nice rig setup. The propellers are off because, safety. But we'll be able to showcase some controllers that we're deploying. So, make sure to ask questions as we go through this. We'll be looking at the chat and trying to answer as many as we go through. But yeah, let's get started.
Cool. So let's get into this content we have with some cool stuff that we have been doing across the industries. We wanted to highlight how MathWorks tools like MATLAB, Simulink, and relevant toolboxes are being used by companies like Supernal, which is an advanced air mobility company building these cool air taxis, and how they used our tools recently to simulate their vehicle in the city of Los Angeles. And another example I would like to show.
Before we continue,
Sure.
Everyone on the who's joined the session, we have a poll going on right now just to get an idea who's joining us today. So make sure to answer that. We'll have a couple polls just to get an idea of what your experience is. Have you worked with drones or controllers? So make sure to respond to those. But yeah, please carry on.
Cool. Do you want to talk a little bit more about the second demo we have here?
Yeah, for sure. This is one that we worked with NASA. So Mihir talked about some of our photorealistic simulations that we offer. We also deploy controllers. So with NASA, they were building out a more precise or accurate or agile controller. You can see them test landing, roll doublets, and this was all done through Simulink. They modeled their platform in Simulink and then deployed controllers onto the drone, did some testing, which I'll show you today, but then, of course, do flight testing at the end.
Awesome. So I think the poll must be there by now. We really want to learn more about what your background is, if you are still learning about UAV applications or already into the research phase, or a hobbyist, or working as a professional in the industry. So please take the poll and we'll move forward here. So going into the why behind this live stream today. So we really want to propagate the thought of the importance of simulations for validating and even before flying your drone out in the fields, why is it important to validate your models with simulations? So there can be a lot of different extremities, like unexpected environmental conditions.
Right.
You have these drones autonomous, the algorithms might not behave the right way. There could be sensor failures like loss of GPS signal or IMU malfunction. And we really want to simulate all these situations in advance and to predict the behavior of the drone in these situations.
Right.
Some other cases where we test the drone in a lab-controlled environment. So even after simulating it in virtual environments, we don't go out and fly the drone directly. We would do it something like this. It's a very quick setup, but also the other one that you see in the slide here, it's a whole gimbal that we have attached the drone to simulate or test out controller errors, mechanical failures, or varying payloads and the drone's behavior for that.
Right, so you can see there's simulated behavior, so you can test out autonomy. You can see that screenshot right there where we actually imported buildings from a certain city. So if you're doing like package delivery and you want to know what buildings you'll encounter on your route. Or on the other side where you can test out well, what if I get a sudden wind gust and because it's a gimbal, we can start actually moving the gimbal, applying external input to see how our platform will react. In this case, it's a little more, you only have 3 degrees of freedom. You don't have as much as that gimbal. And you're locked in certain axes. You can't really go all the way. But it's a really easy setup to start testing some of these things before going to a much bigger, broader test rig.
Yep. So sit tight. We have all of this going to come further in the live stream, and we'll go deep into MATLAB and Simulink to actually how to implement and build these simulation environments and controller deployment workflows. All right, so I wanted to quickly go into the integrated workflow that we really showcase with our tools here. So we start with a system architecture where you would define requirements for the system, and then we go into modeling the UAV. So we have tools to model the dynamics of a platform. It could be a multi-copter, fixed wing, or a hybrid like VTOL aircraft. And then we go into designing algorithms. So we provide out-of-the-box autonomy algorithms from perception, planning to control. And further, we also have workflows to verify these algorithms or certify these algorithms, such as for DO 178 certifications. And you would also like to simulate all these algorithms as we saw in the previous slide. So we have multiple ways you can simulate and connections with these simulators, such as Gazebo or Unreal Engine, directly from Simulink. Then finally, we would also like to deploy the code on the hardware, such as PX4 Autopilot or NVIDIA compute boards. And there are some workflows in this live stream that we will discuss towards those end. And we also have ways to interface with the drones and connect with these drones, as well as the ground control stations.
Right. Just before you go on, we already have some questions, so I want to take one really quickly. A couple people asking about Autopilot, because we've been showcasing PX4 here. We have support for Autopilot coming soon. So if you're working with Autopilot, I'd say about a month we're going to start supporting Autopilot in a pre-release version. So stay tuned. Today I'll be working on PX4 and showcasing PX4 architecture, but soon even Autopilot will be supported.
Yep.
Sorry, carry on.
And I think my taskbar just went up because of a notification, and my slide is not visible fully. But that's fine. We'll have this slide back again. So you can also analyze data, because we have a lot of data coming in and going out in these applications. So we have very interactive apps where you can bring in your data and analyze with visuals and plots. And further, we have reference examples, because it's a lot of different moving parts. So we put together, package them into reference examples that helps you step by step to implement all these different pieces. So we have 2 reference examples, one for package delivery and one for VTOL application.
Right. Just to add a little more context there, again, we want to showcase both autonomy behaviors and controllers for specific platforms. And that's kind of how we built out our reference examples. So if you're interested in autonomy behaviors, we have one for that. And then if you want to build out custom platforms like maybe a tail sitter or a tilt rotor VTOL platform, both can be showcased using our example. It's a great starting point for you to kind of think of, how do I build out the representation of all the systems involved? And we'll share some links to that too, so you can get started on those.
Yep. And so as we talked about a lot of different things that you can do with MATLAB and Simulink, but you might be also working with a lot of other tools outside of MATLAB and Simulink, such as Unreal Engine itself or algorithms from OpenCV. And there are multiple different external simulators, one of which you might be already working with. So how does they fit with the MATLAB and Simulink ecosystem? So I really like this slide, because this really tells how we position our tools more like an integration platform. So specifically for the drone ecosystem, we interface with a lot of these open source communities like PX4 Autopilot, Autopilot. You can bring in different compute boards like NVIDIA, Jetson. You can interface with ROS, Unreal Engine. So really, MATLAB and Simulink sits as an integration platform where you can bring in all these different pieces and use one single model to run all of them together. You can do that for various different types of applications and platforms. So going into what are some building blocks to start with to build a UAV simulation. So you would want to design and model your plant dynamics, flight controllers, autonomy algorithms. Then you'd like to simulate them in photorealistic environments. You would also like to bring in waypoints or inputs from a ground control station.
Right.
And finally, you'd like to deploy it on an autopilot and test out the behavior. So how does all this fit into a workflow? So we have put together this flowchart that explains that how we structure the workflow here. So you see we have inputs from ground control station feeding the flight controller, and the flight controller works along with plant model, and we simulate both of them in a scenario simulation photorealistic environment. And you can deploy your flight controller and plant model on an autopilot or a high-speed computer like SpeedGoat. And finally, you can also design and deploy your algorithms on NVIDIA Jetson for a full Hill workflow.
Right, we're going to go into simulation and deployment in detail, but you see there's a lot of different components that are in this. The flight controller gets deployed to your autopilot. The onboard autonomy gets deployed onto an OPC, an onboard computer. But then now you have two hardware that's running, and then in the center you have your plant, which might be your bottleneck because of just compute resources. And that's where you can deploy that to a real-time piece or a real-time PC. So now everything's deployed. You know at what rate each of them are running on the actual target.
Yep. So for today's live stream, we have a couple of focus from this workflow. The first one we have is scenario simulation, and that's where we'll dive deep into now. So starting with photorealistic simulation, we have some highlights like simulating in photorealistic real-world locations, which is really important. And Ronald and I have been recently at the AUVSI Exponential, and we learned from a lot of companies there that they really want to simulate their drones in real-world location and not just like a dummy city scene or an environment. So we'll showcase how you can bring in these real-world locations like a city of New York, for example. You can also add weather effects, simulate sensor models. So let's dive into that. So how does it work with Simulink? What are the building blocks for UAV visualization that we provide? So you really need three basic things: a virtual asset, which can be a drone of any type, a 3D scene, like you see in this visual here, a city scene, and sensor models that the drone is equipped with, such as LiDAR, camera, and more. So we provide Simulink blocks that Ronald will show in a bit that you can bring in a Simulink model and build out a scene like this directly from Simulink, which opens up rendering in Unreal Engine. Here are some scenes that we have built using real-world locations for which we integrate with Cesium platform. And you can see some cool visuals here with different types of aircrafts, even multiple helicopters in a scene.
Yeah, so if you're testing out your flight or landing in like, a rural terrain, or you want to test out a city scene where you have multiple assets. If you see the second one, we have two helicopters that we're providing guidance to, and they're working with each other. All of this can be done by importing those terrain models and testing it out with, some of the physics handled by Unreal, but your platform's physics handled by Simulink or MATLAB.
Yep.
Perfect. So let me switch over. Give it a second while I switch over to my screen. Perfect. I'm going to jump into.
I can get rid of my taskbar.
Yeah, I'm going to jump into a demo here just to showcase Unreal simulation. So this is a project that we built out. This was actually built out for one of our customers. You can see that I have a couple pieces in here. You can see that there's a fishing boat. That might give you some idea. We have what we call a mini drone, and then a Simulink model. And I'm going to go into the model. Now, when you're working with Unreal, you can do this either in base MATLAB or you can do it in Simulink. You have blocks or actual just functions that you can use to instantiate your world, bring in assets such as the fishing boat or a UAV. You can bring in other textures. I'll show you one that we brought in. And because you're working with Unreal, you get access to the entire marketplace. So let's talk about the different blocks here. You can see that there's a scene configuration block. This one actually lets you decide if you first want to work with an Unreal executable. This is important because you don't actually need to install Unreal. You don't need the engine. You can actually have someone who built this just give you the scene as an executable. That's actually what I'm going to do today. But there are couple other options. There are some default scenes that we ship just with our tools. There's a tool called Roadrunner that we ship that you can use to build out your scenes. It's really good for specific roads, assets in that road, building it out. It all happens through MATLAB and Simulink UI, so it's really easy. And then, of course, Unreal Editor. If you have the editor and if you have the engine running, you can work directly with it. In our case, we're going to use an executable that we built and then shipped. So now I can just give you this executable and you can launch the scene. It also sees scene parameters. I'm going to switch from custom to the fishing boat for now, or let me leave it at custom. We can leave it at that and I'll show you what we have. It's actually where your viewporter, so where the camera is going to be. I have a LiDAR that I'm specifying. This is going to be attached to one of my vehicles in here, so you can see the representation that comes from the vehicle. And then there's two actors. So let's go into this one. It's a mask. It's just a collection of blocks that I'm going to get into. So here you can see I have a translation and a rotation that I'm providing to an actor. I'll go into the actor block so you can see how we've built this. This is our fishing boat. And you can see I'm actually utilizing an existing mesh. Here I'm using an FBX, but you can use STLs or other CAD formats. You can bring them in and use that to represent your actor. You can also scale them to a particular size if you want. So it's really easy with a couple lines of code to bring in a mesh, attach it to an actor, and now you can provide translation, rotation. If these actors have multiple frames in them, you can actuate different frames too, which is really nice. This actor, though, it's not a custom actor. It's one that we've shipped directly from MATLAB and Simulink. So you can see it's slightly different. It's actually called the Simulation 3D UAV Vehicle. I'm still providing translation and rotation to this. And here I get to decide, with our block, you get to decide if you want a quadrotor, or fixed wing, or a custom actor. That means you can actually bring in your mesh itself. Then I can go back.
That's a really quick way I really like about it is if you just want to test your algorithms and need just a quick way to do that, you can bring in a out-of-the-box actor like this.
Right.
And then further, you can bring in your actual model through Unreal Editor.
Right, right. So to start off, I would say start using the ones that we ship because it's going to be really easy to kind of build out your scene. You have multiple sensors that you can use, LiDARs, cameras, you support radars. So you can just instantiate IMUs, start building out algorithms. Really, in 5-10 minutes, you can have this set up. All right, let me go ahead and run this scene so you can kind of see what the visualization looks like. Oh, my taskbar is sitting up too.
The first time when I saw this workflow, I was like, is that it? Because usually I've seen big Simulink models simulating these type of workflows.
All these lines and all connected together.
And here you see like just 4 blocks and you get really cool scenes like these.
Yeah, it's actually really easy to instantiate. So what you'll see is this is our ocean scene. Of course, it looks like there's nothing in my ocean scene right now, but we're actually having actors in this. I just wanted to show you the ocean scene as a base, what it looks like. And then I can go into the actual actors and show you, ooh, I think I lost some control on my once the scene launched, which is funny.
And we saw in previous slides that we also have city scenes and airport runways, highways, a lot of different types of scenes shipping out of the box. So it really depends on what application you're working on, and you can really start quickly with one of these out-of-the-box scenes.
Right, and you could have seen there, we had a LiDAR that was showing some LiDAR data too. It makes it really easy to build out this really quickly and to showcase this scene. So this is like an Unreal scene in which we have these individual actors. Let me run that again so you can actually see the actors too. I'd like to show another demo too. Maybe I'll put my scene origin on my UAV. So instead of having the camera kind of just free floating around, I'll attach it to my UAV, and then you can see, what would this look like from the point of the UAV itself? So give it a second. So now you see I'm looking at this from the UAVs. I've attached a camera at the back of the UAV, and then I have a fishing boat underneath it. Now, once you attach this to the UAV, of course, you don't have the same freedom to be able to move this around as you'd like. But then if that's what you want to look at, you can. I want to show you one more thing. Of course, when I close it, it's going to throw an issue saying, hey, I didn't complete. Let me go ahead and attach my LiDAR to my UAV too. So now I'm going to attach my LiDAR to my UAV, and I'm going to run this again. It's going to show you the UAV right on top of, so I'm going to keep my LiDAR viewpoint open too, so you get an idea. Let the scene load. The LiDAR is actually looking down, so that's why you're seeing this as it sees. Right, so right now the UAV is kind of further away from the actual shipping boat itself, or the fishing boat, not the shipping boat. But then as soon as it starts coming into view, you can kind of see that, okay, now I see the boat in my view. Can maybe one of you give me an idea of what this could be? What was the reason we built this? I'll look at the chat in a second, but I'll give you the answer. Here we're trying to land our UAV on the actual fishing boat. So we have to extract the LiDAR data, find a reasonable place to land, and then generate a trajectory for the UAV to go. Because I'm not showing that, I really want to showcase what we can do with Unreal and how easy it is to build out a simulation environment with such high fidelity, textures of the ocean, assets that you can bring in from anywhere. Yeah, so with the simulation piece, I want to open this up for questions. If you guys have questions about how I built the scene, how we can bring in different meshes into the scene, is this just UAVs, or if there are other platforms we can, we do. We have cars, UAVs, planes, multiple other actors that we can bring in that's available with our tools itself. So yeah, let me see what questions you guys have, and would love to answer some of them.
So there was a question, is there an out-of-the-box fixed-wing and/or VTOL UAV actor? I shared a link in the chat for our example, which shows the VTOL asset. And yes, we do have a fixed-wing asset as well. You can use either of the three.
Yeah, as I mentioned, we have either the quad or we have the fixed-wing asset. I'll show you the fixed-wing asset here in a second. It was in one of the slides itself, so I wanted to showcase that. This is actually an asset that you can use directly from our tools. You can start with this. You can see it's a single prop plane. So the asset itself, you can let Unreal handle the physics, or you can take over the physics. That's what we'd recommend. You would take this actor, look at the actual propeller speed. You would look at the forward velocity, and that would dictate how much lift you're generating and how you're translating through the scene. But thank you for the question. That's really great.
The question was from Tim the Plane Man. I really love the name. We have another question. Is it possible to create bounding boxes to detect objects with the LiDAR data?
Yeah, this is really great. Do you want to answer that, or I can take it too?
Go ahead.
So first you would have to train out a detector based on the LiDAR data to see what cluster of points you would want to label and say, this is the target that I'm looking at. And then when you actually do your inference, you have LiDAR data coming in, and if it sees that same type of cluster, it will generate a bounding box. There's a nicer way what we can do. LiDAR is great at telling you what distance things are at, but it's not really good at telling you what those are. So we actually bring two things together. A camera, which is really good at telling you what things are, but not great at telling you how far things are. So we use like image-based or frame-based detectors to identify what an item is, and then we use LiDAR data to say, what's the depth of that item? So when we have a car versus maybe a truck, we can kind of look at our camera and say, this looks like a car, and then take the LiDAR data, see how much data or how deep that car is, and then create a bounding box, a cuboid that we fit around it. Similar to that, we can do it with a truck. So now your bounding boxes can change in 3D based on your camera's inference and then your LiDAR detector's inference. There's an example that we'd love to show you that does exactly the same.
There is a quick question on how to connect Unreal Engine with Simulink. So the way that Ronald showed to bring those boxes, that's it. Unreal integration is basically bringing in those Simulink blocks and doing those quick settings, and you don't need to download anything else other than Simulink and the required toolbox, which is Simulink 3D animation, to build an Unreal scene. And further, if you want to do customizations, then you would need Unreal Editor to work with.
Right, to customize your scene to maybe you have specific things in the editor that you want to customize, that the editor can do. But if you want to just bring in assets like, put in a boat, put in LiDARs, put in sensors, that we can do directly from Simulink. If you notice the ocean scene that I showcased, I actually imported that ocean scene in the editor, shipped that. So in that first scene that I showed, there was nothing, just the ocean scene. And then I ran it with the additional things that I added from Simulink. And of course, you don't need any tools other than Simulink itself and its associated tools in Simulink.
Another question, is the simulation of the boat and the ocean running on the ThinkPad, or is it hooked to an external GPU?
Actually, it would be it runs really well on the ThinkPad itself. This one does not have a GPU. It's really nice to have a discrete GPU if you're going to run some photorealistic simulations. You can still run it on the ThinkPad. It would just run at a lower rate. Now, that's actually a really good question because it transitions to another piece that I want to talk about. In case of launching Simulink directly from, or launching Unreal directly from Simulink or the editor, we are time synchronizing both of them. So if you have Simulink running at a certain rate and Unreal is not able to keep up because of your GPU is not powerful enough, we'll pause Simulink, let Unreal catch up, and then run it. So we time synchronize both of them, the execution of both of them.
Yep. Can we do HITL? Yes, and we have some cool demos and webinars already on our website. We'll put a link in the chat, or it will be in the slide at the end, so you can go and watch that webinar to look at our HITL workflow.
Okay. Do you want to now move into the second session of this?
Yep.
And we will thank you for all the questions. I think they're really great. Just to make sure that we have sufficient time to go through this, I want to make sure we take some of our questions. Do you want to finish off by talking about some of the additional capabilities?
My slides now.
Yeah.
All right. So Ronald showed us the demo for simulating with Unreal Engine. Oops, I have the wrong screens. All right, let me try
Give us just a second.
So I just wanted to close this off with some more capabilities that we have for simulating with Unreal Engine. And right now you see horses and my screen. My laptop is acting funny. Here we go.
Yeah.
Cool. So in the beginning, I told about the package delivery example that we have. That's a really good one to bring in a lot of pieces, and some of which we already talked about, like taking waypoints from ground control station, environment and sensor models, obstacle avoidance, flight controls, and plant model. So we talked about the environment and sensor models piece right now, where Ronald showed the demo with all these Simulink blocks that are available to build these scenes out. And what more you can do with these scenes are you can include harsh weather like rain, fog, and you can also add time of day.
Yeah. So you can kind of see in the LiDAR data right there, it does have some of the reflections from that water droplets that come through. So the noise that you would experience when you have these rain effects, maybe where the sun's positioned, the brightness of the scene, all that is brought in as sensor data, so you can build out more robust algorithms.
Absolutely. And then these are not the only ways you can simulate. For example, sometimes you might need something quick and dirty to just test out your algorithms, and maybe you don't have access to a GPU for faster rendering. For various reasons, you might want to keep your simulations at a lower fidelity, for which we provide these cuboid-like scenarios as well. So there are really quick ways to build out scenes, these cuboid scenes, where you can also simulate sensors like LiDAR and radar, and perform different simulations to test out your tracking algorithms or obstacle detection algorithms before even going into the higher fidelity scenes. And if you want to really build a big scene using this cuboid world, we have an app called Scenario Designer app, where you can build a full city scene really quickly in this interactive app. That you can also bring in trajectories and fly the UAV within this city to train your algorithms.
Yeah, so the building information from here that you see in here is actually imported from OSM. So you don't have to reconstruct all of this, but the scene makes it really, the designer makes it really easy to say, I have one platform that's going here, maybe a couple other platforms that are flying in other directions, and one will be instrumented with sensors to do maybe like detection and avoid.
Cool. So we wanted to end this section bringing back the Supernal story we showed in the beginning and show you this cool demo that we built with them. So here you can see their aircraft, which they actually provided us the asset, and we imported it in Simulink using Unreal Editor. And then we had these trajectories that are visualized with these green markers in the simulation. Right. And you also have the cockpit view on the top, which is time synchronized, so you see the pilot's experience as well. And it is actually flying in the city of Los Angeles, and we were able to bring the city as well as rendered the colorful textures of the city scene using Google Tiles. So you can actually bring in all these multiple pieces in Simulink for this simulation.
Right. All right, I can take it over from here.
Sure.
So now we're actually going to switch over to our second portion of the workflow. We're going to talk about controller deployment. Give it a second while it moves over. If you guys like Firewatch, that's a wallpaper from there. And I don't actually know the game, but someone just told me when I was switching, they saw that wallpaper and they're like, you play Firewatch? And I was like, what is that? But sorry for the distraction. The second workflow is actually going over controller testing and deployment. So we talked about simulating it with either a low fidelity scene or really high fidelity scene and how quick it is to build out those scenes. Now we're going to talk about plant modeling, analyzing log data, and then tuning and deploying controllers, or maybe building some additional supervisory controllers. And I'll show you some examples. I'll deploy to this platform and show you how that works. Great. So let's talk about plant modeling. Now, before you can start building your controllers, you want some rough estimate of your plant. This can go from a really low fidelity one, like we provide a guidance model. This is an approximate model of an expected plant, like a fixed wing or a quad rotor. You can see we can provide control actions to this, which would be roll, pitch, yaw, and then you have an environment input too, which is you can either say you're on the moon and gravity is changed, or you could say there's a lot of wind coming in from the east. How would that affect your plant? Right, so that's a really quick way to start building out your whole piece with the plant, and then you start building your controllers. But then of course you have a higher fidelity, which is going to like a 6DOF block. Now there's two pieces here. I'm going to talk about the first one. It's a point mass block, and you're going to provide forces and moments to this point mass. The forces and moments are going to be based on your actuation surfaces. So you would say, hey, if my ailerons are lifted up, I'm going to have a force at a certain distance away from the center or the CG of my platform, right? So your equations are going to define how your platform reacts based on the actuators or the motors that are running. So you can build that at a really high fidelity. And then of course you can see there's also additional sensors that we provide, lapse rate models if you want to look at baro, airspeed, really high fidelity if you want to build. And then going even further, if you want to build, if you have CAD models that you can then import, which means masses, inertias, moments, all come in from that CAD model, you can start actuating these individual models. I can start saying, this propeller spins at this speed, which is going to generate thrust at this point, and then start seeing that platform move. This is using one of our tools called SimScape Multibody. So it knows that this is a rigid body that's attached. If I apply a force here, it's going to create a moment and spin it around. So it's really high fidelity because it brings in your actual platform, and then you can start instrumenting it where your actuation, what kind of forces are going to be applied to this based on your actuation. All right, so I talked about the plant. and how you would build out a plant. And there's multiple representations. Once you have that, you would start building out your controller. Now, everything right now is in simulation. And you can see a ground station attached there too. When you're working with open source flight autopilots, they usually have a ground station to define your mission, to look at how many GPS satellites you have, to maybe decide what channels of your actual RC, radio transmitter, you want to utilize for different things, and I'll show some of that. But this is still all in simulation. Everything's a model at this point. And then we move on to software in the loop. Now what we do in software in the loop is we generate code for your actual flight controller, and then we run that on your host machine. It could be a ThinkPad, it could be another desktop PC, but we're making sure that the model and the generated code perform exactly the same. And then once you've verified that as a software, then we go to hardware in the loop. This is where we move that piece of generated code onto your target device, which means now you just have the compute resources of that target device. Like I could run everything I want on a server-grade machine and do really fast response control and navigation. But then I move on to a much more low-powered machine, and I'm like, wow, I'm not getting the frames that I want. I can't control it as quick as I want. So you do have to test it with your actual platform to see what kind of compute you're able to get. At what rate can you run certain things? Maybe lower the rate of some higher level commands and make sure that your low level or your inner loop is running at the fastest rate so it's stable. So these are things that you can do while going into hardware in the loop. And we've actually been working on support for some open source autopilots. You can see a couple listed here. The PX4 is one that we added our past release. CubeOrange also we've had for a while right now. In our newest release in 24A, we're supporting PX4 6C. We're supporting the CubeOrange Plus. These are all directly supported. They're supported with PX4's 1.14 firmware, so control allocation is available now, which I know a lot of people have been waiting for. But if you don't have any of these platforms, we still support them. As long as they can work with the PX4 stack, we can support them. And that's kind of what I want to showcase here today. If you have a piece of hardware that's unsupported, how'd you go about it? So here, what I'm using is an M-Robotics MRO Control 870, or Control 087. It's the non-OEM version, so it comes with actual plugs that I can plug things in. And I want to showcase how you can actually build this out. That's going to take a second. Before I do, I want to talk about one more piece, which is flight logs. Now, the most important thing, I think, is after you've built out your controller and you've deployed your controller, you need to come back to simulation with your recorded data. Now, we have a lot of tools in terms of control design and parameter estimation. And what they help you do is, say I told my simulation to roll 45 degrees, and then I see the response of my simulation based on my simulated plant model. Then I'll go fly my actual quadcopter or my platform, whatever it may be, and do the same 45-degree roll, and I'll see how my actual platform responded. So now I have simulated data and I have flight log data. I can bring both of these into Simulink, and then I can run parameter estimation to see what parameters should I tune to make my simulated plant exactly the same as my actual plant. This way you have an accurate representation and you can do very precise tuning before you deploy it and try doing, maybe a flip. You don't just want to roll, you want to do a flip. You could break your ass at doing a flip. So make sure that you've used your flight logs, gotten the right estimation of certain parameters. When you're doing parameter estimation, I would try to take an educated guess for some of the parameters like wheelbase, wingspan, distance of CG from each of the rotors. These you can measure. These are easy to get. But like coefficient of drag, coefficient of thrust, these are a little harder for you to estimate really accurately. So those I would use parameter estimation to actually get the right values of. So here I want to take a second to talk about flight log analyzer.
So before you do that, quick question.
Yeah.
Can you add payload to UAV in MATLAB to performance, stress analysis, and stability of payload?
Yeah, this is a really good question. So payload is going to change a couple things, right? It's going to change the moment as you spin around certain places. It's going to change the overall mass. It's going to change your endurance of your drone. So these are all things that you have to look at. How quickly can I do a roll doublet now? So based on which model you've used, I would go through either the second level of fidelity or the third level of fidelity. In the third one, it's really simple. Create a block mass, attach it to the bottom of your UAV. In the second one, we would actually change some of the forces and moments because it's a point mass. I would change the mass of that and also maybe look at, because that mass is not exactly centered in the CG, you would bring it a certain down and you would know if you were to apply a force or a moment, how that would affect. So yes, you can add payloads. You can look at, if you start modeling out the mechanics and the electrical battery models, then you can also start to see at what rate are you depleting your battery with this added payload. How much does your endurance go away? Really good question. Yeah, cool. So did you want to go for some more questions or should I continue here?
No, I think that's good. We want to leave some time for the drone demo as well.
Yeah, true. Okay, so let's talk quickly about Flight Log Analyzer. This is a really nice app that we've built. We recently added support for bin files from Autopilot, but T-logs, U-logs, even custom flight logs, we can import them. We can start looking at individual signals, axle, gyro. You can time span them. So if you saw like maybe halfway through the flight, you saw this weird motion and you want to like look at, what was it? Was it one of my IMUs telling me, one of my EKFs going bad? This is a really good way to actually look at this. And the really nice part about this app is once you've set it up to where you really like looking at, maybe you want to look at axle data along with XYZ local position. And then once you set this up, you can actually save that session and then forward that directly to someone else, and it'll open exactly how you were looking at it. So they don't have to fudge about, recreating the plots or pulling in data. They just have to open the session, load the log file in, and they'll immediately see what you were looking at. Great. I want to take a second to go into plant identification. I talked about this earlier. So you can see here we have two plots, roll rate, roll, and pitch. And of course, there's log, a set point, which is what we actually provided, plus the simulation. So this is what I was talking about, where you bring in your log data and your simulated data, and then try to match them as closely as possible by estimating parameters such as maybe your inertia matrix, maybe your drag coefficient. Those are the ones we'll try to tune. So you set a lower min and a higher max, and then Simulink will automatically sweep through all the set of combinations to give you the lowest error, which will tell you what a more accurate value for these coefficients would be. We actually have a demo that we built just with that. So here I was actually flying the drone. I got some flight log data in. First I did open loop testing to make sure that my controller does exactly what I need it to, because being the PX4 architecture, I can start looking at what was the RC commands, what was sent to the controller, what was the roll pitch yaw commands that came out of the controller, and then also post-mixing, when I have to decide which motor gets what value, what was that value too. So I can start, make sure my controller is doing exactly what I expect it to do, and then I can go and make sure my plant is doing exactly what I wanted it to do, and then I can deploy this onto it. So here's another example that I wanted to showcase. We deployed two types of controllers to this, one being a detuned acrobatic mode. So acro by itself is pretty aggressive. We detuned it. And then we also had a more tuned stabilized mode. Stabilized just means when you leave both your roll pitch toggles, it'll come back to center. Okay, now it actually came time to go ahead and do some deployment work. So just to get things set up, let me open up one of the controllers that I've been working on. It's fairly straightforward. So you can see with UAV Toolbox and PX4 support package. Oh, this is not, I think I'm sharing my wrong screen. Let me make sure I'm sharing the right thing.
Right, so a couple of other questions here.
Sorry about that. Now you should see this. Yeah, do you want to take a question before we jump in?
Sure.
That'll give me a second to also go ahead and plug in.
So what about simulating randomly walking pedestrians?
That's a really good one. I actually forgot to mention that we do have pedestrians. So
Yep.
we have an asset for pedestrians. So you can go and add a pedestrian, add a trajectory for that pedestrian. We're going to actuate the person. Maybe he's running across the road. Maybe he's walking by the side of the road, really close to the car itself. But yes, we do have pedestrians. Really good question.
And minimum requirements for a PC to run Unreal Engine. I'm just putting that link in the chat, which will give you all the information you need for your computer requirements to run the Unreal Engine simulation.
Perfect. Okay, so jumping right into this, this is controller safety. This is actually another controller that I built. You can see that I'm reading from my radio controller. I'm looking at a specific channel, channel 8. And what I'm doing here is, this is when I give people the drone to fly, I generally don't want to give them 100% of the power. So I use the toggle channel 8 to say 25% power. So you can see that I'm reading this, I'm saturating that value, and then I'm actually taking the actual outputs that come from my actuator motors. I'm reading the control values, and then I'm dividing that by whatever threshold that I put. So I would give them 25% by dividing it by 4, and then slowly give them 50%, 60%. So this way they get the full axis, but then they don't get full power. So they don't have to move a little, but they can move all of it and kind of learn, just have muscle memory of how to fly this before I give them 100%. You can see the model is really simple. I'm reading from a certain actuator message. I'm actually pushing that back as a PWM output, but then I'm reading one more channel and utilizing that to cut down how much is actually sent to the actuators.
And reading and writing these messages that exist out of the box from UAV Toolbox,
yeah,
right?
Everything that you see here is Simulink and UAV Toolbox. The ones that actually have PX4 attached to it reads a micro-orb message from PX4. We support both Mavlink and micro-orb. Micro-orb runs inside the flight controller, and then of course Mavlink is a way for you to connect to the flight controller when it's running through telemetry. Yeah, so these are actually provided directly from our toolbox, even the radio transmitter.
Are you connecting into flight controller or flight computer? So I think it's flight controller.
Right. Good question again. This is actually being pushed to our flight controller. A flight computer would run higher level commands. That would be something like an NVIDIA Nano that's reading from higher frame rate sensors like a LiDAR, a camera, and then it would send an OBC command. That runs at a much lower rate, generally at like half a second, but the flight controller runs much, much faster at 1 millisecond. So at 1,000 hertz or a kilohertz is what that runs at. This is connected to the flight controller or the Autopilot, and this is what I'm actually going to deploy right now. So again, I'm reading from another micro-orb message. I'm looking at the attitude, which is, a quaternion roll pitch yaw is defined by that. I'm going to pull this out. I'm going to do some check. I'm going to check that the quaternion is valid before I do anything. I want to make sure that I don't want to take any bad readings. Then I'm going to actually convert that into roll pitch yaw, or here it's YPR, yaw pitch roll. I'm going to actually provide a desired yaw, which I'm specifying as 0. You can specify this to any value that you'd like. And then I take that yaw and I provide that, that's pre-mixed commands coming out of here. I mix that to generate motor commands, right? So I'm just saying, what is the yaw? I want it to go to 0. And a very basic controller that I've put here. I have things disconnected too. I can just delete that. But just a game-based controller. It's very simple to actually make this a PID-based controller. Here I'm just doing a proportional control. It's very simple so that we can ship these models to you. So if you're trying, you can see this. So I have a controller actually coming in here. This controller is only enabled when my channel 8 goes higher than a certain threshold. I think the threshold that I put is 1500. So channel 8 can move between 1,000 and 2,000. So if I move over 1,500, more than half, then I'm actually going to supply this yaw control. Otherwise, just like before, I'm just reading actuator motors, which means whatever I'm getting from my RC is going to get sent directly to my actual drone. Now there's one more piece I want to talk about here. There is the build, deploy, and start, which means it's going to build the model, generate the code, move it over to your flight controller, and then you can fly it. But there's also something that we call monitor and tune. Now, because this is not a directly supported controller, there's a couple things I want to show you. So let me go back into MATLAB, go to my add-ons, go manage add-ons. Will I be able to bring this back? There you go. So I'll go to manage add-ons, and I'll go to UAV toolbox support package for PX4 autopilots. I'll go into the setup screen. This is how you would set it up first. When you start building this, you would run through the setup screen. As soon as that launches, let me just minimize this for a second. Make sure my setup screen is up. So here you can see that it's making sure that I have the right firmware. So I can click validate. It's going to take a second to go through that. I think the scaling, just make sure you can see everything big, kind of makes this a little glitchy, but I'm going to go over to that. So confirmed. And then it's going to ask, do you want to disable the existing controllers? I'm going to say no, I'm adding to this. So I don't want to disable the existing controllers. And this is where if you had a supported one, you would just pick that. You would say, hey, I want to work with the PX4. Those are a little hard to find now, but maybe the PX6X. But if not, you can say my board is not listed here, and then you can hit browse. This way it's going to open up. You can see I have WSL loaded. We'll share a link with how to set these up. It's really simple. We have all of this really documented. But then here you have all the other boards that are available. I'm going to go into MRO. I'm going to say mine's a control 087, and I'm going to use the default PX4 board, CMake file, and then hit open on that. And then it'll let me build my firmware. Once I build that firmware and I go back to my model, you can see here, it tells me that I'm connected to PXOC series, which it knows if I open my hardware settings, you'll immediately see that I have PXOC series, MRO is added as my CMake configuration. So one thing for MRO that I want to specify, I'm going to go into Device Manager really quick. Oh, glad it could auto-spell that for me. And I want to show you something. With specific autopilots, you'll see that it says USB COM5. I'm going to unplug this right now. It's going to disappear, so now there's nothing there. And then I'm going to go and plug it back. It's going to take a second. It'll refresh. You'll see that, okay, COM4 has shown up. But then as soon as the autopilot starts, it becomes COM5. So this is something that you should be careful with when you work with autopilots. Sometimes the bootloader has a different serial port than the actual communication port. And in MATLAB or in Simulink, you have to specify that. So my COM4 was my bootloader port, but if I was going to do external mode, that's COM5. Make sure that's correct. Once that's correct, you can go and do monitor and tune. Right, this is going to take about a minute to build the firmware and start deploying the firmware. So this is a good time for us to start with questions.
Sure, yeah, there are a couple of questions that came up again because we didn't answer them earlier.
In the meantime, I'm also going to go ahead and put my battery in here because we need power before we start doing anything with this.
So can you run Simulink and Unreal Engine on two computers connected via Ethernet? Have you tried that earlier?
Oh, that's really cool. So if you have Simulink, you would have Simulink on both of them. So what you would do is, from one Simulink, you would send out a UDP message, and on the other Simulink, you would read a UDP or TCP/IP, just any network protocol. You'd be communicating over from one PC to the other using a network protocol, and on one you will have your platform dynamics, on the other you'll have the simulation piece. But yes, you can. All right, let me quickly go into this.
Yep.
So now that it finished building, it's going to tell you to reboot. So I'm going to unplug my autopilot. I'm going to click OK, and I'm going to plug my autopilot. I'm going to plug my autopilot back in.
Communication lost.
Now it's going to actually reboot. So now COM4 is going to open up, and it can flash that firmware onto the drone itself. So as soon as it finishes building, it's going to start beeping at me saying that it's ready to go. And I'll plug in my battery, and I'll show you one way why monitor and tune is different from actually build, deploy, and start. Great. So what it's telling me is the target has been built. It's ready for me to actually utilize. I'll take that time to go and plug in my battery onto this. And of course, I need my RC controller.
Welcome to OpenTX. Switch warning.
So you can see that now I'm running this model. It's telling me that it's running already. I've actually instantiated this with a couple log. So you can see I'm logging this signal, I'm logging these signals. So let's look at what does this controller do. You can open up Simulink Data Inspector. Give it a second while it launches. Oh, why is that out of screen? I'm going to try to close that. For some reason, it feels like it's out of screen. Let me launch it again. I'm going to just swap screens for a second because I think the presentation mode is taking away my Simulink Data Inspector. So I'm going to, you want to move over to yours for a second?
Yep.
All right. Let me make sure my Data Inspector is up and ready.
So while Ronald is setting that up, I also wanted to show some other stuff like obstacle avoidance workflows we have. And this is one of the demos we have that brings both the scenario simulation as well as the deployment piece together. So here we are showcasing a hardware in the loop workflow with the obstacle avoidance algorithms. In the top window you see on the right, it follows the waypoints and it does not follow. It does not include obstacle avoidance. So in the simulation, it just passes through the tree. However, in the bottom one, the obstacle avoidance algorithm takes over the controller and let it avoid the tree.
Yeah, it's a really neat demo where we showcase in Unreal how you can bring in sensor data and start building algorithms. All right, I'm gonna jump back into mine. It should showcase my data inspector now. So you can see this is my yaw value that's being presented, and if I move this, you should start to see the yaw value kind of move around. And you'll also see, because I have my battery, of course I haven't armed the drone yet, but you can see how these yaw values are changing. So now the flight controller is running. I'm gonna go ahead and showcase, if I move, it was yaw control, right? So if yaw goes to one side, I have 2 of the motors shooting up, whereas if yaw goes to the other side, I have 2 of the other motors. But that enables with one of my switches. So I'm gonna enable the switch, and I'm gonna also zoom into this so you can, let me do a time zoom so you can see what I'm actually showcasing. All right, so yaw on top, that gives me my current yaw value. I'm gonna change my yaw, I'm gonna get it to 0. You'll see all my motors have fallen down. Now if I start yawing this side, 2 of my motors will turn on, saying that, hey, come back. And then if I yaw to the other side where my yaw falls under 0, the other 2 motors will start shooting up. Right? How cool is that? This is a way for you to make sure while you're connected that your actual controller, your attitude controller knows what it's doing, your motors are going to perform the way you expect it to. All right, now that you have this running, I can actually remove my cables. I can go ahead and restart my drone itself. Because I deployed this earlier, And then I can show you if I were to run the drone. Of course, when it's sitting with yaw 0, it doesn't care. It's not going to do anything. But now I can start actually activating my drone. You can see right now I have full control. Whatever I do, I can move it here. It's not gonna do anything. It's responding to me. But then, because of channel 8, I can go and turn on channel 8, and you can see this. It is working on the actual moment of the drone itself. So if I were to move it this way, it's on the other side, and then I enable yaw control. It's going to bring it to the center. Then I can disable it, and I have full control of the drone. I can do what I want. See, I'm using the moments of the actual motors itself to move the drone because I don't want the propellers running here.
We don't want to break the studio.
But if I use channel 8 and I enable yaw control, it's going to now direct it. It's going to apply sufficient moment to bring it to the center. I can disable that. I can move it to this side, and then I can enable yaw control again, and then it's going to try to bring it back again. So let's do that again. Yeah, but then if I turn this back, the drone's mine to use. I can control it how I want.
So you're switching back and forth between manual control
and stabilize mode by using one channel that I decided that I wanted.
Cool. And we can, while you're doing that, we can also visualize in the Simulink data inspector
what's actually happening. So you can see in the data inspector, well, once I actually unplug this, you can't, but in Monitor and Tune, what you want to do is utilize your data inspector, make sure that the signals that you expect when you are yawing, maybe let's call this minus and this plus. When you're in minus, you have 2 of the counterclockwise ones spinning to turn you back, and when you're in plus, you have the 2 clockwise ones spinning to bring you back. Yeah, so first make sure you do it with Simulink Inspector, so you know, data inspector, so you know, is your attitude controller giving the right data based on the current yaw? I'm still reading from these sensors. I'm still sending data to the same motors, but I'm just making sure that everything works before I go and plug in my battery. And then I can plug in my battery and do the same test with my actual flight controller. And then once I'm happy with that, I can take it off this rig, I can put the propellers on, and I can go test it in actual flight.
Very cool.
Yeah. All right, we have a couple more pieces to go over, but maybe what we can do now is take a look at some of our questions. Because I know we're running a little over time, but maybe I'll talk about this example and then I'll go into the...
Yeah, so this is a really good one to talk about now, since we have seen how you can do some testing within a lab environment.
Yeah.
But what NASA did outside the lab environment and actually went and flew the drone, what was that they did?
Yeah, they used the same process where they first tested out, they built their controller, they had an idea of what their plant looks like, they tested everything out on actual, in a lab setting where it's reading data in Simulink. Then they tested it out just connected on a 3 degree of freedom rig, and then they went and did the same test with actual propellers outside. So you can see if I replay this, they made sure takeoff was stable. After they took off, the controller that they were improving was roll and pitch doublets. So here you can see they're doing a roll doublet. Of course, when you start rolling a drone, you lose some thrust, so it's going to lose attitude or altitude. And that's what they were making sure. When they roll, they don't lose any altitude. They want to stay at the same altitude. They actually gave us a really nice quote that I like showing a lot. They said, this solution made it easy to take a Simulink developed controller and implement into a flight vehicle. In the past, hardware integration was difficult. Now we can deploy and test a new flight controller in minutes. They said it took weeks before, and now it takes minutes. They're actually working with the Cube Orange. They've just moved to a newer version of that. But we have a blog post. We'll share a link.
Just put a link now.
Great. We'll share a link to the actual blog post to showcase, how they went through this. They have 2 white papers that they've released to talk about the different algorithms that they've pushed.
Awesome.
Yeah, I'll leave this running while we take a couple more questions. We're pretty much done with most of our
Yep.
content that we wanted to showcase. So if you have any questions about what I just demoed here, how the controller worked, how I built out my channels so that I can turn on and turn off control.
There was
please-
one
please shoot.
question that came up 2 times. Is Simulink auto linearization app able to reason about quaternion dynamics?
Right, that's an interesting question. I'm not a controls person, but I know one of our developers had to use that for different trims. So this was for our VTOL, vertical takeoff and lift reference example that we shipped. And in that, hover mode, fixed wing flight, forward transition, backward transition, they're very non-linear dynamics. And what he had to do is take each of those individually, build, take an operating point, linearize it about that operating point to build out a controller. So he took that work and then used our auto tuners to give him the best gains to control those.
Cool. Another one here is there any explicit requirement to select a certain airframe in QGC prior to setup in MATLAB to enable all main and aux PWM output channels?
This is a really good question. And yes, there is a requirement that in QGround control, when you have your platform connected, that you specify what your airframe is, what kind of aux channels are you going to send data to. So here, I'm going to try to share my screen again so I can showcase what that'll look like. So let me just stop presentation mode for a second. And then here you can see QGround control. With the MRO, there's a specific thing that I have to do. I have to go and actually connect to the COM port that MRO is going to come through. Give it a second. It sometimes takes a second to actually connect. But once it does, you are able to go into your vehicle setup and specify the airframe, specify different things like where are your motors? What is motor 1, 2, 3, 4? What PWMs do you want to send to them? We actually have ways of increasing. So in QGC now you'll see maybe there's 8 motors, 8 servos. If you're on 1.14, we have a way of actually making that more, go up to 22 or 30 different servos, 30 different motors. But yes, you do have to specify what airframe, what RC are you connecting with, what kind of battery levels, it's a 4S, 6S. If you want to learn more about this, we'll be happy to connect with you offline and kind of give you an overview. I don't think I have the time to do that right now.
Can we also use Mission Planner?
That's a really good question. So if you were going to work with Mission Planner, you can do that with Autopilot or PX4. Generally, people use that for Autopilot. I personally haven't used Mission Planner for a couple years now, but there should be no restriction. You might have to build out your own Mavlink client to connect to it.
Awesome.
Yeah.
I think we're almost 15 minutes past the end
Yeah.
time, so we can end it here with the summary slides.
Go ahead. Do you want to take over and jump into the summary slides?
Sure. And yeah, for the summary, we just have a couple of advertisement for our next webinar and some resources to share. We learned a lot today about simulating in virtual environments, photorealistic environments with real-world locations. And then Ronald showed us some cool demos in a safe lab-controlled environment, deploying drones directly from Simulink to PX4 Autopilot. So I think it was a lot of content you saw today, and we wanted to just finish up with these 2 reference applications examples that we have. One is for the package delivery we talked about, and then the other one is for VTOL, where you can bring in a VTOL asset, simulate it, deploy controller for it. And we have an upcoming webinar on June 25th, where you can learn more about deploying controllers for VTOL airframes. So we'll post the registration link in the chat, so please go ahead and register for that. Really cool stuff there. And then here are some other resources. We have shared a lot of these links already in the chat.
Right.
So you don't need to type them in by looking from here. But you can also either take screenshot of this QR code, scan it later.
Yeah.
If you're on a computer, scan it now. And
Yeah.
this will take you to our solutions page, which includes a lot of information about our UAV solutions. And then there is a link to this past webinar. We will put it in the chat, where you will learn more about hardware in the loop simulation and even real-time simulation and deployment using speed code.
Yeah, a lot of great resources that we've put out, so make sure you check them out.
Awesome. So I think we can call it to the end with this.
Yeah, thank you so much, you guys. A lot of really great questions. I hope you enjoyed the demo. We'll be putting out more of these hardware demos just to get you guys acquainted with how to work with autopilots.
Yeah, feel free
thank
to
you
put
again.
it in the chat if there is anything else you would like to see another live stream on. We'll be happy to review that and plan for it. Otherwise, it was really good talking with all of you. Thank you so much for all the questions.
Yeah, thanks again. Have a great day, everyone.
Have a good one. Bye.